Okay, so we started looking at this standard discussion you see for green functions, starting with the time-dependent Schrodinger's equation, and showing that this expression for the green function, I guess, underlined in the brackets times minus IH bar, and all of this stuff does indeed satisfy that equation of motion on the top line. And so we just worked through it, I thought, somewhere. I guess this is where we worked through it, sort of. And we finally show that if you just, take your DDT and act on that thing, you do indeed get a delta function. That's equal to a delta function. So this is indeed the time-dependent green function satisfying that equation of motion, circled in red. And this is the first time you've seen something that's a function of time instead of energy. And the way it's written here, this t minus t prime, that's going to be true in steady state, in which it's only going to be a function of the time difference. So you can define two types of time. One is like the time, the sort of equivalent of the center of mass time. You'd have a t equals t plus t prime over 2. Sort of the way you define center of mass in relative coordinates. And in terms of this, nothing is happening. You assume the system is just not changing as a function of time, and that everything only depends on the time difference. And again, the interpretation of this green function in terms of time is the same as our interpretation in terms of position previously, where if I hit the system at t prime, it tells me what happens at time t. Okay, it's the impulse response. I apply an impulse at t prime, and it tells me what happens, what the response is at time t. All right. And to then go from time to energy, we simply Fourier transform this time difference coordinate. So I'm just going to start anew. So to go from time to energy, the green function we've been working as is a function of energy, gr of E. We simply Fourier has a Fourier transform minus I over h bar. And we need some kind of convergence factor, so limit as eta goes to 0 plus integral. Remember, this green function in the time domain is defined with that unit step function, that theta t minus t prime, and so that gives us this bottom limit, integral from 0 to infinity, d of t minus t prime, e to the minus I h t minus t prime over h bar, and then my Fourier transform pair with this convergence factor, e to the I e plus I eta, e plus I eta, t minus t prime over h bar. So we're just asked to do that integral. And since you have that convergence factor, you just do it just like you would any exponential. So that's equal to negative limit eta goes to 0 plus of this exponential e to the I e minus h plus I eta over h times t over h bar times the whole thing times t over h bar, t over h bar, where when I'm writing this, my t here is really t minus t prime, over the denominator e minus h plus I eta, evaluated from 0 to infinity. And the eta factor kills off the limit at infinity. That's why it's there. It's your conversion factor. And at 0, the exponential goes away. And so you just have that that's equal to the limit as eta goes to 0 plus of this e minus h plus I eta inverse, which is probably a definition that you've seen before for a green function. Okay, so this is our GRB. So the first thing to do is when you see something like this, you ask, what is its, where are the poles? So the poles are going to be, if this is energy, the poles are going to lie when E has a small negative imaginary, right, this I eta. So let's say this is my 0. They'll be all along the real axis. Where they are on the real axis is not too important. It's just where they are on the complex plane, right? They're all offset slightly into the lower half plane because of that I eta term. That was your, the purpose of your convergence factor, so you can, close the integral on the upper half plane. At any rate, the important point is that the poles are in the lower half plane. We'll come back to that. So your retarded green function is analytic in the upper half plane. So if I were to do a closed contour integral of the retarded green function in the upper half plane, I'd get 0. And that's actually used later on, that fact. If we consider what they call an eigenfunction expansion of our retarded green function. So an eigenfunction expansion, let's see, how does this work? So we just assume we've got this complete, a set of complete eigenfunctions, we'll call them n. These are all the eigenfunctions of the Hamiltonian, all the eigenfunctions of h. So Hn is E sub n, n. So these are the eigenfunctions of h. And so an eigenfunction expansion of this gr of E, what have I got to do? I've got to do this, sum n m. I hit it with an identity on either side, so I'd have like m, m, and then my E minus h plus I eta inverse, and then n. Right, that would be an eigenfunction expansion. I just put in the identity operator on either side of it. And so, well, the only operator in there is h, and so wherever h hits an n or an m, you just replace it by that energy. So this is equal to sum, I'll keep my limit now, I limit as eta goes to 0 plus of sum over n and because the Hamiltonian is diagonal in this, in the eigenfunction representation. So E minus E sub n plus I eta. So this is what's called the eigenfunction expansion of the retarded Green function. And here, if you look at these, it's, the analytical form is really apparent. It's just E minus some real energy plus I eta. So the poles are all going to be when E has a small negative imaginary part, again, in the lower half plane. So the poles, right, the poles are specifically when EP, that's a pole, would be an eigenenergy En minus I eta. Right, those are the poles of the retarded Green function. Slightly shifted off the real axis into the lower half plane. Okay, so the poles are in the lower half plane. Now, for those of you who remember your undergraduate EE work, and you all took one course out of control theory, you probably, if you're like me, have some Pavlovian response to this, LHP, when you're doing control theory. I don't know if that rings a bell. In control theory, that stands for left half plane. And in control theory, you work in the S plane, the Laplace transform variable. And when the poles of your system were in the left half plane, it was a what do you want to say? A well-behaved system, right? The response would die out as a function of time. It was a causal system. If the poles were in the right half plane, it would oscillate, and it would oscillate, I think, forever. It was in, I forget what you call in control theory. Say that again? Yeah, so if the poles were in the left half plane, it was a stable or damped system. It would have some real, exponential decay with time to the response. And in the right half plane, it was unstable. It would oscillate. So in the left half plane, if your poles were in the left half plane, it meant, there was some part of the response that would go as like e to the negative t over tau. Some stable system. And if the poles were in the right half plane, then it would grow with time, like e to the plus t over tau, and that's bad. Right? That's an unstable system. So the question is, all you learned about stable and unstable systems, and now we're talking about the analytic form for our Green function. Let's make the connection. So S, your Laplace transform variable, is I omega, which is equal to e to the I pi over 2 times omega, where omega is our frequency, right? Our frequency variable. And just to be clear, E equals h bar omega. Right? So that's how you map from the S plane to the omega plane to the energy variable. I mean, energy and omega are just the same within a constant of h bar. So the S plane is a 90-degree rotation of the omega plane. Right? S is just rotated by 90 degrees from omega. So if we take our omega plane of our causal Green function and rotate by 90 degrees, where do the poles end up?
Imaginary axis?
What's that?
Imaginary axis?
Yeah, but on which side of it? That's the important question.
The 90-degree counterclockwise opposite, so it will be on the right side.
Yeah, it'll be in the right half plane.
Still,
The poles will be in the right half plane. Okay, and now from your semester of control theory, you should immediately start being concerned. Like, what's going on? Right? We've just shown the poles in our energy plane are in the lower half plane. If we rotate that by 90 degrees, they end up in the right half plane in our S domain. And from all your control theory, which most people forget quickly, but if you haven't forgotten it, if you just remember left half and right half plane, you know that that's not good to have poles in the right half plane, right? That much should kind of come back to you, that right half plane is bad, left half plane is good. All right. So what's going on? Well, what's going on is that physicists and electrical engineers have different sign conventions for frequency. So for an EE, for our electrical engineer, we do our Fourier transform like this. We say f of t is equal to integral d omega over 2 pi of e to the I omega t f of omega. And I'll label this FEE of omega. Right, this is how we do our Fourier transform in the electrical engineering department. Over in physics, they say that f of t is equal to integral d omega over 2 pi times e to the minus I omega t. F tilde physics. And so what that means is that when you go from EE over to physics, that omega of physics is negative omega in the EE department. So what that means is that the green function in the EE department, the poles are really in the upper half plane because our omega is the negative of the physicist omega. So from the EE perspective, the poles of our retarded green function are in the upper half plane, and when we rotate by 90 degrees, they're in the left half plane, and all is good. So it's this different sign convention. Now the reason we have this different sign convention is because electrical engineers develop all their theory to analyze signals. And so, doing this, if you're just analyzing a signal, makes sense. You just, you got all your Fourier components of your signal, you weight them by their weight, you sum them up, and that's your f of t, right? Makes perfect sense. Over in physics, what they're usually doing is expanding some phenomenon in terms of a plane wave. So they're expanding in terms of e to the I kx minus omega t. They're expanding some spatial temporal function as a function of plane waves. And so when you look at it like this, it naturally shows up as e to the minus I omega t. And this is why, when you do quantum mechanics, you got one sign convention for the spatial Fourier transform and the other sign convention for the time to energy Fourier transform. So, we in physics you have f of x, let me see if I can get this right, is the one you would expect, integral, do it in one dimension, dk over 2 pi e to the plus I kx times f of k. So you add up all those components like this, but you have f of t is the other sign convention. integral d omega over 2 pi e to the minus I omega t f of omega, right? It's one of the first things you sort of stumble upon when you're doing quantum mechanics, that there's these two different sign conventions for Fourier transforming time and space. And the one in K in space is sort of the one we think of, where you just sum up all the wave components, e to the ikx. But there's this opposite sign for time because really they're expanding in some plane waves, set of plane waves like this. So that's the last piece of the puzzle, so it's all good. It all corresponds to what you've already learned, that this is a causal green function. The poles are where they should be to have a causal response. Nothing's blowing up. And it also, this is something to remember because this has actually caused real confusion when people calculate, do some physical simulation and then try to extract a capacitance or an inductance. And the way capacitance and inductance are defined, at a fundamental level, is in terms of a phase lead or a phase lag. And so depending on the sign of your omega, what looks like a phase lead can be a phase lag and vice versa. And so people have associated inductance with capacitance and vice versa. And there's been big arguments in the literature and et cetera, due to physicists and electrical engineers, a small difference in sign convention. Okay, so that's the retarded green function in the time domain. And the advanced green function is the anti-causal one. And it just, everything, well, okay, I'll just write it down. So GA of t minus t prime is equal to I over h bar, e to the minus I h t minus t prime over h bar. And it's anti-causal, so we have the other step function going the other way, t prime minus t. And we Fourier transform that. The Fourier transform of that to energy will be G A of E is I over h bar, integral from minus infinity to 0. And so the sign of the I eta term has changed because now we're integrating from minus infinity to infinity. And I need it to disappear at t minus t prime. It goes to negative infinity. And so that's equal to limit as eta goes to 0 plus, again, of E minus H minus I eta. Before it was plus I eta. Now it's minus I eta. So now the poles are going to be in the upper half plane, right? A little off the real axis in the upper half plane for the advanced green function. And in fact, they're complex conjugate of the poles of the retarded green function. Right? We do the same eigenfunction expansion, and we would have just some n E minus epsilon n minus I eta limit eta goes to 0 plus of all this. All right, so the poles are complex conjugates of each other. And this is what we said that, when we added, we get the spectral function by adding, it's like we do I times GR minus GA So what does that mean? That means GR minus GA. So the real parts are going to be the same. And I just get, what do I get? I just get I times 2 imaginary, and that I out front kills it off. And so I get the spectral function. And the spectral function, if you think about that, since it's the sum of GR and GA, and they have poles that are complex conjugates of each other, it means the spectral function is going to have a poles, complex conjugate poles, both above and below the real axis. Complex conjugates of each other. So it's not going to be analytic in either, anywhere, in any plane, any half plane. If you want something that's analytic in a half plane, you need either a retarded or advanced green function. Okay, symmetry properties. Let's look at, we write down the green function as sort of a general operator, right? When I write it as E minus H plus I eta inverse, H is an operator. And then I can take different representations. So let's look at it in the real space representation, which you'd write like this. Okay, that's going to be G of, what that means, that's G of R comma R prime at a specific energy. That's what that means. So that's, again, that's the response to the system. If I hit it at R prime, what's the response at any other position R? And the way we make sense out of it is we use our Eigenfunction expansion and just hit it with R and R prime on the left and the right. And just to make it perfectly clear, that's limit. Where these phi's are the eigenfunctions of H. Right? Phi's are the eigenfunctions of the Hamiltonian. And this is the standard sort of eigenfunction expansion that you see in any textbook when they first start discussing green functions. It's sort of a classic form for the green function. So first let's consider no magnetic fields. And so you have time reversal symmetry. And in this, let's consider a couple of cases. So in one case, in a confined system, then you can always write it where the eigenfunctions are real. Phi n are real. You have real eigenfunctions, and then phi n and phi n. I mean, it doesn't matter whether I complex conjugate doesn't matter. And then clearly, G of R comma R prime is equal to G of R prime comma R. Right? That's obvious if the eigenfunctions are real. Because phi n equals phi n star, right? Okay, that's an easy one. The next is if the eigenfunctions are complex. I don't know, what's the symbol for complex? I'll just write it out. Like plane waves, for example, right? That would be a perfectly fine set of eigenfunctions, plane waves, where they're complex. But then, in that case, the sum over n includes, since we're summing over all eigen states, it includes both phi n and phi n star, since both phi n and phi n star are eigenstates of H. And therefore, at some point that phi n star of R prime up here, at some point this term in the sum over n will become phi n of r prime, because the sum runs over both the eigenfunction and its complex conjugate, because it's running over all eigenstates. Right? And when that happens, this one will become phi n star, because you're summing over all of them. And so again, because of this, you also get that gr of r prime is g of r prime r. Is symmetric in r and r prime. And this is a general property of the green function. And, well, of course, it also applies to the advanced green function also. Once you turn on a magnetic field, this is no longer true. I need to update these notes. Okay, so that's enough. But this is the most important one that most textbooks immediately talk about. That gr prime is gr prime comma r. This symmetry. In other words, if you hit the system at r prime and look at the response at r, it's the same as if you hit it at r and look at the response at r prime. Physical point of view. So I guess this section on calculating the green function of a periodic 1D array of atoms, I guess you already did that for your homework. I guess we just did the diagonal elements, so I'll just say a few words about this. So for your homework, any questions on the homework? So for the homework, I think you calculated just the diagonal element GII. For this 1D, this ideal 1D chain of atoms. So if you extend that, I think maybe we do this later when we talk about the recursive green function algorithm. In general, for our 1D chain model, Gij is just I over gamma, or I is negative square root of 1. In that case, I over gamma times a plane wave, but not, it's got an absolute value in here, e to the I Ka times the absolute value of I minus J. So it only depends on the difference of site I and site J. And we see the same symmetry in this case. In fact, you can go back in the same analysis in terms of the symmetry, that if your eigenfunctions are real, and your basis states are real, then you also have the same kind of symmetry between them. And our gamma is our usual, the same gamma you did for the homework. It's h bar, v for whatever k you're at, over a. And I think we're in these notes right near the end of the chapter. I just show that this does indeed satisfy the equation of motion for the retarded green function. But we don't need to go through that. So that brings us to the end of chapter 1. And I think at this point, rather than writing down all this as a summary of equations, I'll just talk through. So we've covered a fair amount of ground, and in fact we've derived all the basic equations that are used in non-equilibrium green function theory. And in this, right at the end of the chapter, I summarize them all. And a lot of, even though the derivations were simple, limited to 1D, these 1D chain models, and purely coherent transport, the final form of the equations that we calculated are actually much more general than their derivation. So for example, all these, 149 through 159, all those equations are completely general. And if the self-energies represent both the contacts and some incoherent scattering process, then this is still the same form of the equations. All right, they're completely general, whether you include some scattering process or not. If you were to include phonon scattering, then it would just add to that self-energy term. It would be incorporated in that self-energy term. And you would just have, a self-energy sigma r due to the coupling to the contacts, and another one due to the phonons. If you wanted to, you can just represent it all as one big self-energy. So that is the completely general form, what people call the equation of motion for the retarded green function, the advanced green function, this G sub n, this, we call it there's no good name for it, electron correlation function, because it's really not a green function. It's not on the right-hand side, that third equation down, right? It's not an identity matrix. It's not like a delta function, Kronecker delta or something. So it's a correlation function. And it can be written as two ways, both 151 and 152. So the 151 is sort of the equation of motion. 152 is just multiplying through by gr, since the equation above it is gr inverse gn equals sigma nga. Right? That E minus H minus sigma is just gr inverse. So you multiply that through by gr and you get the next equation below it. Same for the whole correlation function, G sub p. As we've just seen by that Eigenfunction expansion very clearly, the advanced green function is gr dagger. What we haven't seen, but what's also true, is that the sigmas follow the same relations as the g's, so sigma r is sigma a dagger. And the relationship between the spectral function and the green functions is the same as between gamma and the sigmas. So just like A is the spectral function, the total number of states, gamma represents sort of the total lifetime due to, in Superdata's book, he refers to sigma n and sigma p as in-scattering and out-scattering. So gamma is like the total scattering, all scattering processes, both in and out of the state. If you think of a phonon type scattering process, I come in my K state and I can emit a phonon and go to some other state. That's one lifetime. Alternatively, another electron can come in a state K prime, absorb a phonon, and go into state K. That's another lifetime. So the in and out scattering process, the gamma encompasses all of them. That's like the total scattering rate. Just like A is the total number of states. And both of them are Hermitian. A equals A dagger, gamma equals gamma dagger. The next, so the relationship, we always get the charge density by integrating Gn over energy. The only thing that's specific about these is that they were written for our 1D model. If you were in a higher dimension, then you'd be dividing by a volume instead of a length. You would be taking a trace. If you had multiple orbitals, you'd be taking a trace over all the orbitals within the unit cell, something like that. But this general relationship, how we get the electron density will always just be integrating G sub n over energy. That's how they're related. Same with the hole density, integrating G sub p over energy, and this relationship that you went through in the homework between the spectral function and the density of states. These equations up top are true, these are specific to equilibrium, but in equilibrium they are always true irrespective of whether you have incoherent scattering processes or not, ballistic, non-ballistic, diffusive. These four equations are always valid in equilibrium. And, you know, it's pretty, if you think of A as like the density of states, it's just saying that, you know, get the electron density, you weight the density of states by the Fermi factor, which seems pretty straightforward. Same with the whole density. To get the whole density, you weight the density of states by 1 minus the Fermi factor, which seems a pretty reasonable thing to do. And as I keep saying, the relationship between the sigmas and the gammas follow the same pattern as the relationship between the G and A, the G's and the A up above. So I can never remember whether sigma n is in-scattering or out-scattering. Let me think. So I got to think of it in terms of sigma n is... So sigma n is like the in-scattering, and it's related to the total scattering by F times the total scattering. Let's see if there's a simple way I can... If that's the in-scattering... Yeah, I can't remember exactly how that works for the sigmas right now. The in-scattering and the out-scattering. But at any rate, you can see they follow the same relationship between the sigmas and the gammas as the G's and the A's. Okay, and then, so everything up to now are just very general relationships that, you know, are far more general than our derivation. And then we get down to stuff that is only valid for coherent transport, such as, you know, this right here. I mean, this is only true for coherent transport because the only self-energy terms are coming in from the self-energies on the leads due to coupling to the leads. And they're written actually very specifically for this 1D type binding chain model. And these are the actual form of the self-energies. And this is for our little 3x3 model system. We've been focusing on the relationship between the wave function amplitudes, the green function, and our gamma. This is the general way you get the current. Again, for a ballistic system, it's only valid if there's no like phonon scattering in your device. It's what we've been doing. The relationship, how you go from the transmission coefficient to the current. And the transmission coefficient is what we calculate on the next line from our green functions. And our gammas that we get from our self-energies. So there are two forms. This one we derive, which people refer to as this Fisher-Lee form for the transmission coefficient. And this more numerically efficient one that we derived afterwards, where you only need the first block of the green function to get the transmission. Because calculating inverses is time consuming, and there are numerically efficient ways to just get, you know, certain elements, especially the like upper left and lower right corner blocks, you can get very efficiently, far more efficiently than just inverting the whole thing. So that's current and how we get current from transmission. Then electron density, how we get the electron density from these left and right injected spectral functions. And, you know, the left one was just GJ1 gamma 11 G 1J star. It was like GR J1 gamma 11 GA 1J. And the similar form for the right injected spectral function. And, you know, these are like, the left injected spectral function is like psi squared that you inject from the left contact. The right injected spectral function is psi squared that you inject from the right contact. You weight them by their, you know, the statistical probability of them being filled, right? The Fermi factor of the left contact and the right contact, and you sum them up and you get the charge density at site J. Same, and then a more numerically efficient way, again, where you only need to calculate the left injected spectral function, and this you get from the diagonal elements of the green function. So at most, instead of calculating the whole inverse, we only need the diagonal elements of the green function here, because this is -2 imaginary g jj, right? That's the relationship between the spectral function and the green function. So we need the diagonal blocks only, and this we get from the first column of the green function. Did we write that down somewhere? This we get from the first column of the green function, right? Row, column. So column 1, we need the first column and all the diagonal blocks, and that's all we need as long as we're only doing ballistic transport to get both the electron density and the current. So that summarizes everything we've done so far. So I guess now, let's see what's next. So this, this last page of this chapter is a good thing to keep around if you start working with this stuff. Ah, yes. Okay. Now we get into the good stuff. That was all. Like, how do you actually go about calculating this stuff? Okay, so first in chapter 2, we just start looking at the overall structure of the system equations that we need to solve, because you've got this finite region, and this is a region you need to get the electron density and all that. But you got these two semi-infinite regions on either side, which in our very simple 1D chain model we were able to handle analytically. But in general, as soon as you go beyond that, you need to do something numerical. And so this is, we develop all the methods that the most common methods used to calculate what's called the surface green function of the leads, and from the surface green function you get the self-energy that we've been using, that we need to take into account the leads. So to begin with, let's just consider a device that only has a left lead. A device with just one lead, a left lead. It's not much of a device, but we can demonstrate all the concepts with it, with a left lead only. And so the form of your equations would look like this. I've got the basically semi-infinite matrix of the left lead over here. E minus HL, L means the Hamiltonian of the left lead, okay? And this is going to be coupled to the device by some coupling matrix. The left lead couples to the device. I'll put the device, and I've got so here's my part from the device down in the other corner, which is finite, something we can actually put into MATLAB. Minus T LD. So that's the structure of the matrix, and this is going to be acting on the overall. I'll write out all the terms for the green function. We've only been focusing on the device part, but you'd have a green function of the lead only. You'd have a green function that takes you from the device to to the lead. And these are all, big block matrices. And finally, you have over here what you really are looking for, the green function of the device. I mean, that's what you're after. All the rest is stuff that you have got to figure out how to deal with it, because they're actually semi-infinite blocks. The only thing that's finite is that block, the DD block, down in the lower right. And that's going to equal that's your identity matrix out here. Your identity matrix. All right. So that's the general structure in sort of block matrix form of what we're looking at, what we have to deal with in general. And so the important thing is we only want GDD, and we don't really want the other three blocks, GLL, GLD, GDL. And we can do this, just by using algebra. So let's just look at, write out what these equations are. We've got, just two rows, so we've got two equations. And we have, if we write this out, that E minus H sub L acting on G, E minus HL, which one am I doing? I guess I'm multiplying this column times the first row of the matrix on the left. So I have E minus G times GL comma D minus TLD times GDD is equal to 0. Right, that's what that gives me. And then I multiply the same column by the second row of the matrix, and I get minus TDL GLD plus E minus H sub D times GDD is the identity. And we use the top equation, this guy, to solve for GLD in terms of GDD, and then substitute into the equation below it. So GLD is equal to E minus H sub L inverse times T LD GDD. And then we substitute this into the equation below it, and I get that minus TDL E minus HL inverse TLD GDD plus E minus H sub D GDD is the identity, and just by substituting. And now, well, all the terms multiply GDD, so I get the GDD, which is what we're after, is equal to E minus the device part of the Hamiltonian minus TDL E minus HL quantity inverse T LD. I think that's it, and then the whole thing inverted. Okay, so what I've managed to do by writing it like this is I get just what I need. I get, I start off. I mean, if you ignore the fact that this is actually an infinite matrix, let's assume that this block is, just for the sake of argument, that this block were finite size. But say nevertheless, the only thing I really want to solve for is this block over here, GDD. And in general, matrix inversion is what they call an n-cubed process. The number of operations goes as n cubed. It's a really numerically inefficient thing to do. So what we've done is, what I've just done is written down an expression to get just, what we desire, GDD, without calculating all the other stuff. So by doing this, I cut down the number of calculations a lot. And, well, in our case, this block over here is actually semi-infinite, so I have no choice. But nevertheless, this is an example of what they call inversion by partitioning. So if this were finite size, then I end up inverting, right? This whole thing in brackets is now being inverted, but the size of it is only the size of h sub d. The size of what I'm now inverting is only the size of h sub d. Okay, so I'm inverting something much smaller than the entire matrix, and that's a good thing because, as I said, it scales as n cubed in the inversion calculation. This is called inversion by partitioning. And the best, well, I mean, that's really all there is to it, just using algebra to sort of solve for one part in terms of the other, and just get the solve for the part of the matrix that you want, one corner block or the other. But if you also notice, the form that we've just calculated looks pretty familiar to us. E minus H minus something. By definition, that something is the self-energy we've been calculating. Yeah.
ASD is kind of 3 to 3 matrix.
Say that again?
ASD, the device Hamiltonian, is kind of 3 into 3 matrix, right?
It's kind of what?
3 into 3 matrix.
Well, that's what we've been doing, yeah. 3, that's, yeah.
And the E minus HL, it's semi-infinite matrix.
Right.
So how are we adding the 3 to 2 matrix with
Yeah, well, those TDL matrices are pretty asymmetric too, right? L is semi-infinite and D is 3.
Multiply that, then
Yeah, it turns out. So the whole thing is D by D, which is 3 by 3. Right? When you multiply matrices together, it's the outside things. Right? So that whole thing is 3 by 3.
So, yeah, so T is also a matrix.
Yeah, right. Yeah. And everything we do is going to finally be tight binding. So these T's will actually only couple the last, that if you're looking at the left lead, the last node in the lead, node 0 of the lead to node 1 of the device. That's the only thing is coupling. We'll get to that. So, by definition, this self-energy due to that lead is just this TDL E minus HL quantity inverse. That's our self-energy due to coupling to the lead. And this is exactly what I was just saying. So if you think of what this means, break it down into indices. So sigma r dd I comma j is going to be equal to, so I'm going to use Greek indices for those that are in the left lead. So sum alpha equals 0 to minus infinity, sum beta or gamma 0 to minus infinity of t dl tdl I alpha. So the Roman indices are in the device, Greek indices are in the left lead. Okay. E minus H left lead inverse, and then the alpha gamma indices of that, since that's all in the left, that's the Hamiltonian of the left lead, times T L comma D gamma J. So this would be the actual, matrix multiplication you would be doing in terms of the actual indices. So I and J are in the device, alpha and gamma are in the left lead. And as I just said, the only non-zero matrix elements that couple from the device to the left lead, I alpha or gamma J, are the 0, 1, and 1, 0 matrix elements in all cases for everything we do, no matter what, whether this is a three-dimensional structure or a simple 1D type binding chain or whatever. So the only non-zero matrix elements are your T10 or T01. So those are the only non-zero matrix elements that couple the left lead to the device. And so that collapses that sum over alpha and gamma, and we get that sigma ij is equal to TDL 10 E minus H D, that H, HL, sorry, HL inverse 0, 0, and TLD 0, 1, and Kronecker delta I comma 1, delta J comma 1. So the only non-zero matrix elements of this sigma due to coupling to the left lead is just the 1, 1 matrix element as we did before in our simple tight binding model. And now we've gone through this much more generally. So there's a lot of, concepts being demonstrated. One is that we have this E minus HL inverse, which looks like a green function for the left lead. But to get the self-energy that I need for the device, the only element of that semi-infinite green function that I need is just the 0, 0 matrix element, the matrix element of the node right next to my device. I need one element out of that whole thing is what I need. That is what's called the surface green function, which if you've ever read any sort of non-equilibrium green function stuff, There's always some comment on that somewhere. So this is your famous surface green function. It's the green function of the left lead, but right at the surface of the left lead, where you have, basically cut any matrix element coupling the lead to the device. And it's just that H sub L doesn't contain any matrix element that couples the lead to the device. It's sort of a hard wall boundary right there at the end of the left lead. And then you just have the matrix elements that couple that last node of the lead to the first node of the device. And this is the general form of the surface green function that we will be looking at a lot. So the general form that people write this down as is that sigma, due to this coupling to the left lead, 1, 1, is equal to T10 G. I'm going to call this is a retarded green function, but I'm giving it a special name for surface. It's a retarded surface green function of the left lead, T0, 1. That is the general form of our self-energy. And we're going to show that it is exactly what we calculated before. So just to, previously, we calculated that sigma R was equal to negative, I think it's negative magnitude T, e to the I. Ka. And therefore, our surface green function in this simple 1D model, 1D chain model, has got to be equal to e to the I Ka over T. And it looks like we're going to derive that. Okay, so we're going to look at a couple of different algorithms, because this is actually one of the more time-consuming parts of the calculation, getting the surface green function to calculate that self-energy. This is the very first thing you need to do, because you need this to just construct that matrix from which to solve for the green function of the device. So before we start talking about the iterative algorithms, let's take a break.